This video is on hydroboration oxidation. Hydroboration oxidation is another two-step process to add water to an alkene. This method won the 1979 Nobel Prize in Chemistry. It is as follows. You take an alkene, and in step 1, you react it with borane, B₄H₆, and tetrahydrofuran, and in step 2, you add hydrogen peroxide and sodium hydroxide to it. You end up with this alcohol product. Note that the addition is anti-Markovnikov. The alcohol has added to the less substituted carbon. This is why it won the Nobel Prize. How is it possible though? Well, recall that boron is less electronegative than hydrogen. So when you have a boron-hydrogen bond, the boron is partially positive and the hydrogen is partially negative. Therefore, when an alkene attacks, it attacks the boron instead of the hydrogen. Due to the instability of a hydride anion, though, the hydride will then attack the carbocation that would be forming when the alkene is attacking. So this all happens simultaneously. The hydride transfers to the carbocation as the alkene attacks the partially positive boron. This is referred to as a concerted reaction. Once we have the boron attached to the carbon, we can then replace it with an oxygen from the hydrogen peroxide sodium hydroxide reaction. If you think about it, technically this still does follow the Markovnikov rule, as the electrophile still adds to the less substituted carbon. It just happens to not be hydrogen in this case. But for all intents and purposes, when you look at the final product of the two-step reaction, we don't care what caused it to go there. We just know that it's on the less substituted position, which we refer to as the anti-Markovnikov position. So once again, long story short, depends on how much detail you want to put into it. The product is anti-Markovnikov, even though the reaction mechanism itself follows Markovnikov. Another quick tidbit, you will see borane as B₄H₆ or as the dimer B₂H₆. Because of the difference in electronegativities, the partially negative hydrogens like to coordinate with the partially positive borons, so they form these dimer systems. So don't be stressed if you see B₂H₆ instead of B₄H₆. They are the same chemical, just written slightly differently. The second step will always be hydrogen peroxide and sodium hydroxide. So, what would be the product of this following hydroboration oxidation reaction? You may pause now. And here is the answer. As we can see, the alcohol added to the less substituted position. Sometimes you may be asked to show the intermediate instead of just the product. Or in other words, the two steps of the reaction might be split. So, for example here, what would be the intermediate and product? Well, in the first step, we are just adding the B₄ and H to the double bond. And in the second step, we are replacing the B₄ with the OH. So, what would be the intermediate and product for this reaction? You may pause now. And here's the answer. And finally, as a side note, borane or B₄ has 3 hydrides. So technically it can react with up to 3 alkenes in one go. So when it comes to how much chemical do you need to add to a reaction, it probably won't be a 1-to-1 equivalent. You can save money by just adding 1/3 of the borane. This is more of a bookkeeping thing. Don't worry about it in exams. Just put the one equivalent, as it's more of a practical thing as opposed to theoretical thing. But this is a reminder that stoichiometry still matters, even in organic chemistry. What about the stereochemistry of hydroboration oxidation? Well, due to the concerted nature of the addition, where the borane and the hydride both add to the double bond at the same time, they also end up on the same face. Once the hydroxide replaces the B₄, this is not an SN2 reaction, so we do not see an inversion in stereochemistry. So whatever face you put the hydride on in the hydroboration step, that is this face you will put the hydroxide on also. Now you have a go. What would be the products of these reactions, including stereochemistry? You may pause now. And here are the answers.